In our first example for section 1.3, we're going to talk about how to convert a complex number into polar form. So it's just a quick reminder. If we draw the complex plane, and we have our complex number somewhere, say here, and it's x plus iy, then that complex number, if we were to draw the segment joining from 0 to it, the complex number makes some angle theta with the positive real axis, and that complex number also has some length or distance from 0, the modulus of z. And this modulus we generally will call r for radius. And if you have such an r in theta, you can compute what your complex number is by the usual circle formula that we were talking about in the previous section. And if you have z, you can compute r in theta, sort of. R is, of course, the modulus of z, which we've encountered already, the square root of the real part squared plus the imaginary part squared. And then theta usually will involve some arctangent. I'm not going to write equals because equals is a lie, but it involves an arctangent computation. So, how does that work with this particular problem? Well, we're going to start by computing our modulus, which is r. And so we're going to take the square root. So here's our complex number up here. I'm going to take the square root of negative 3 squared plus the imaginary part's negative 1, so negative 1 squared. And that's the square root of negative 3 squared is positive 3 plus 1, that's root 4, and that's a 2. So our r is a 2, and that's great. Now I said that for our theta, to compute the angle parameter, it should involve some arctangent computation. So let's compute arctangent of y, which is negative 1, over x, which is negative root 3. So that's the arctangent of 1 over root 3. And if you plug it into a calculator or you draw the relevant triangle, you'll see that this is pi over 6. Now, pi over 6 does not make sense for our angle theta because the complex number negative root 3 minus I, scroll up in blue underlined up here, that's in the third quadrant because the real part's negative and the imaginary part's negative. Whereas the angle pi 6 is going to be in the first quadrant. So we're outputting an angle in the first quadrant when we need an angle in the third quadrant. And the fix for this is to add or subtract pi. I'm going to start by adding pi. And we get 7 pi 6. All right, so now we can express our complex number in polar form as r cosine of our angle plus I sine of our angle. And that certainly works. Now, to elaborate here on theta, theta is usually called the argument of z, or an argument, because there's more than one. There's another angle theta that works. So instead of adding pi, which is to say we would draw pi 6 and then do another pi to get us in the right spot, we can draw our pi 6 and then subtract pi. And that will also be an argument which is just as good as the one we just wrote down. So we could have said theta is pi 6 minus pi, which is negative 5 pi 6, in which case z is 2 cosine 5 pi 6 plus I sine, or negative 5 pi 6, plus I sine negative 5 pi 6. That also works. That's just as good. Or we could even just take our theta that we computed in the first one, which was 7. Let me just write 7 pi 6. And we can add in any number of full rotations. So 2 pi k just means some number of 4 rotations. How many? K many. And that's also another way of representing z in terms of polar coordinates. So z is going to be twice cosine 7 pi 6 plus 2 pi k plus I sine 7 pi 6 plus 2 pi k. For any integer k. And so this is a little bit weird, but we've seen this before actually, and you see this when you learn about the square root. So let's do an aside on the square root. So we know that the square root of 4, we usually say that that's 2. Well, that's not entirely true. The square root of 4 can be one of two numbers. It could be plus 2 or minus 2 because they both square to 2. And since it's two numbers, what we do is we have a convention that we will always pick one of them if we want to have a function. So we say the principal square root is the non-negative answer. So we have our convention as the principal square root of 4 is 2. So another way of saying that is principal, I'm going to write square root for square root of 4 is 2. So of the two options, we have to pick one. And the same is that we can do the same convention for the argument, which is this angle parameter. So for arguments, we'll say the principal argument of z is the one that's in the range negative pi to pi. So we'll write that as argz, and this is the one that's going to satisfy negative pi less than argz less than or equal to pi. And the reason why we pick this, so if we were to draw a picture, what would that look like real quick before I go on a tangent? So we want to pick angles here. So we either go negative or we go positive, but we don't exceed 180. And the reason why we pick this as our argument range is, well, first of all, it's symmetric. If we picked 0 to 2 pi, it wouldn't be symmetric. But that's okay. We can forego symmetry. That's not a problem. However, this is a good range where arctangent is mostly correct. So if we were to do 0 to pi, 0 to 2 pi rather, sorry, not only is arctangent going to need to be modified, it's going to have to be extra modified because of the anti-symmetry. Okay, so the point is that this is a good range to pick as our sort of principal argument. And if we were to go back to the example 1 above, the principal argument of negative root 3 minus I is going to be the one in that range. Let's scroll up real quick. So we found 7 pi 6. That exceeds pi. It's not in the right range. But negative 5 pi 6 works. So the principal argument is negative 5 pi 6. And there's one and only one angle in that range that will work, and this is that angle. So this is a principal, again, principal argument.